Hi, welcome back. On session 2C, we have seen a simple two-state model in the last lecture and also a three-state model. Now, we are going to see a full-fledged five-state model which actually explains you the real transition of different states of a process since it is created. And then a six-state model which is an additional add-on to the this five-state. Now, let us see. Now, why do we need such a elaborate state diagram? The reason is actually the processes go through these different states and OS needs to know all of them because there are some things which it needs to take care when a process is in a particular state. Now, let us look at this. The new state is a one is the entry point of a process into the system. Here, what happens is once the process is created, a PCP entry is allotted. The first thing is birth certificate is given, that is PCB allotted. But still, this process is not ready to run. Why? When the PCB is created, it's not enough. Okay, it's an entry in the OS data structure. A PCB entry is given. Maybe a PID is given to the process, a name. But still, it's not ready to run because its own resident set of that new process whatever is created is yet to be brought into the main memory. What I am drawing is a main memory. Hard disk is there. Let us assume hard disk is there. And we need to bring it to this. It's not going to be immediate. It takes some time. So in between this new to ready state, anything could happen. Maybe that particular executable file is corrupted. It's not readable. Okay. Or the path wherever it is supposed to be, when you try to access it, the user who is trying to run the process may not have the access permission to do that. He or she may have a read permission, but write permission is not there. Sorry, execute permission is not there. That you want to read that file from. That program needs to be executed by the user process. And if that execute permission is not there, OS will say that sorry, I cannot execute that file because it doesn't have you don't have a execute permission of that file. So in that case, then the OS will not load it into the main memory and make it run because who is initiating this running of the process could be anybody, could be a user who has the rights to do that or who may not have the rights to do it. So you know that in a system any file may have different access permissions. I will be talking about it later on when we talk about the labs. But at least to understand that each file in the system has read, write, and execute permissions. For a user who is the owner of this process, could be owner of the file, or a user who is initiating that execution of a particular file need not be the owner, but may be a part of the group that person belongs. In that case, each file also has some access permissions as per the group members, or it could be anybody who has a login to the system. This is others. So there are three ways a file can have different ways of access permissions. One is the owner of the file, another one is a group members to which the owner of this file belongs to, and then the other one is anybody else in the system. So each one of them will have different access permission, only read permission, write permission, or execute permission. Now, if our question is like we want to see that we are able to execute it, that means unless you can read the executable file, you cannot execute it, right? So you need to have a read permission as well as execute permission of that file for you to read it, put it on the main memory. You open it up. It's like opening a book and then summarizing it. Okay. So the executable file is a binary representation of how the code is, what are the assembly instruction, binary code of assembly instructions in the file, where are they supposed to be, which part of the memory where they are supposed to be laid out, and then what are the data portion, and there may be BSS segment which is uninitialized data which needs to be filled with zeros. So these are all how much of arrays you are declared. The size of those data element could be different based on how much data global data has been defined by that user. or a developer of that particular executable. So all this need to be understood from the executable, and then it should be laid out on the memory, different segments with the different access permissions, because code wherever it is residing on the main memory should have a read and execute permission. Wherever the data is residing, based on whether it's a const type or a non-constant type, it should have read permission or read and write permission. Then there may be a stack area where, mostly because local variables and parameters are going to be there in the stack, they need to have a read and write permission. If the program is using a heap malloc library, then there is a separate area reserved for it. And mostly malloc, you are trying to give a dynamically memory allocated memory to the uh, process to use it and then release it back to the library. Now if you are giving a memory to a process for it to write into it, right? We cannot give a memory and say that don't write onto it. Then there is no use of dynamically allocating some memory to a process. So those memory which is allocated on a heap using malloc function call needs to be a read write permission needs to be given. Then only the process user process will be able to write into it. So heap will have read write permission, code area will have read and execute permission, data based on whether it's const, then it is read permission. If it is not a constant and you can write into it, it should be read and write permission. Please remember, you cannot write into a area of a memory unless you are reading from it. Okay, you suppose you are incrementing it some variable, then you have to read it, take the current value of the variable, put it into the register and increment it and put it back. So you should be able to have read and write permission. You cannot say that I will give only write permission but you don't have a read permission. Then there is no point of even say giving a write permission, because if I am writing something into it, I should be able to read, right, what I am writing into the file. So or a data area, so I should be having a read and write permission. So these are all the different permissions at the memory level when you are bringing those segments into the memory. So a program has to be brought into the main memory for running, and each of the segments of the program may have different access permissions. So all this is handled by the OS. You don't need to worry about it. OS, with the help of a hardware module within the CPU, which is called Memory Management Unit. We will be talking about it soon in this course, MMU, okay, which is used for making sure that once a particular segment of memory is set to be read and executable permission, then it is only done, those two things are done on that area. If any program, any part of the program illegally trying to write into that part of the code, which is supposed to be only read and executable permission, which is supposed to be having only these permissions, write is not allowed. When it happens, the hardware captures it, catches that particular illegal activity happening on that particular location and writes an exception to the OS, and OS comes to know of it and then informs the process saying that okay, you are trying to do something illegal or someone else is trying to do for you on you. Then it actually stops the person who is trying to do the illegal activity. So it is prevented. If the user process itself is trying to write into the area which is supposed to be not written into, then also an exception will be created and the OS stops it from writing into it and the program gets terminated. Okay, so these are all the things which is happening background. So just to come back on the state, new state is one where PCB is allocated and the resident set has to be read from the executable and brought into the main memory. Once it is done, then the process moves to ready state. That means it is now ready to execute, to be executed. And you know where the main is, the entry point of it. So PC will be pointing at the program counter, will be pointing at the entry point of the program main. Before that, whatever is happening is all taken care of by the OS and the shell if it is Linux environment or whatever. Okay. Now, what happens now after the ready state? What is supposed to be? Then the rest of it, I think this part of it I already have been explained in the previous lecture, right? What is happening? So I'm not going to repeat that. Now, what is this particular state? This is the one where a process has been terminated, exited from the system, and there is a possibility that even the process which has been exited from the system may be holding information about its state. Okay, it's like what was the reason the process was terminated? Is it because of force by force, or because naturally the process has terminated itself, or it did some illegal and then it was exempt, forcibly stopped? It could be many reasons. Okay, so those things will be maintained in the exit state. But PCB may not be reserved for that process because it's still terminated. In Linux, what happens is it maintains it until that PCB is reallocated later on. Sometimes, if suppose the same process comes up, that particular PCB could be reused. Okay, that's very implementation specific. But in Linux, what happens is if you keep observing on Linux environment, when the process is getting created, the PIDs will be keep on incrementing. It's not it will not be reusing the old PIDs. Even if the process has been created and it was having a PID of maybe 100 and then it got terminated, that PID 100 will not be reused immediately. It is any new process getting created will be given a new PID. That means new PCB entry is created. So sometimes the exited processes are maintained in a zombie state where you want to get to know about some information about the process which has been exited. Okay, it could be like a post-mortem analysis of what has happened with the process. Okay, so a new to exit are added here. That's a new states. When a process is created, a new PCB entry is created by the OS, but still the resident set of the program is yet to be loaded into the main memory. So OS cannot run it until the resident set is available on main memory. So when the loading of the process onto the main memory is completed, it moves from new to ready state. Now running state, all of us are aware, it's running on the processor. If it is a single core, only one process could be running. If it is a quad core, there may be four processes running. If it is a dual core, only two processes may be running. I am not bringing a scenario where each core could have multiple threads. Okay, there are recent processes which have a core within which two threads can be running simultaneously. That means what? It has got two sets of CPU registers and two different threads could be running in the same time on a single core of the CPU. So in that case, then for each core, two processes may be running. But we are not assuming that. We are not even talking about the thread support at the hardware level. See, thread support at the OS level is different from thread being supported at the hardware level because a single CPU can run one thread of execution. When the CPU is optimized for or designed for multiple or two threads running on the same core, that means it has two sets of, it's a twin baby. Okay, there are two sets of CPUs registers available in the same core and they identically in the same clock they will be running, but they will be executing two different set of streams of execution instructions and it will be two different threads. So we are not talking about that. In that case, quad core will have four processes at the same time running on the system. If it is a single CPU, it may be a single process. Now, what is a ready process? Ready process is something which is ready state is one which is not having the CPU to run, but everything is available for it. Blocked and waiting, you know that it is waiting for some event. Then each of the transitions, new process, I already told you about it. Exit is a process could have been released from the pool of executable processes by the OS. That means it's terminated either because it halted by itself, because it is aborted maybe for some reason. OS can extract some useful information from the exited process, like a something happens to someone, unnatural death. Then what does the police do? They do a postmortem on the body. So if a process is terminated, OS can look into the PCB entry and try to find out what caused the problem. It could be some illegal instruction being executed, where it is actually, so that the user can debug it and then find out what was the cause for a termination of a process, okay, or an illegal, maybe segmentation fault or some overflow condition or whatever. So that kind of thing is maintained in the PCB. So that is why PCB entry may be still valid even in the exit state. So the exit status helps the process to be in the system occupying the PCB and memory after it is terminated. This is helpful in case of some processes created by the user again. Image is readily available on main memory and it could be reused. Okay, there is a possibility that the image is still there on the main memory. The resident set is available, code and data, maybe entry point of the code and data. Then you can reuse it. Okay, it's very rare condition, but I'm just saying that if the process is getting terminated and immediately invoked, we can reuse the existing thing. Okay, this may be possible. So now I'm going to bring a new state which is suspend state. So you are aware of all these states. Now only this is what is this new one. Why is there a need for a state like suspend? Now let me give a background of it. I told you OS is here and then different processes are occupying different space. Now imagine you are running out of space in main memory. maybe imagine that there are three processes. These are the resident set of the process, and now you can't run more than three processes now. Now imagine a situation where this is in running state. This process which is occupying this space is in running state. That means it is on the CPU, because remember, one of the user process should be running in the system. Sorry, it's not CPU. CPU is here somewhere. Suppose it is running on the CPU, so it is in the running state. Now imagine these two processes are in block state. That means it was running earlier and then it wanted some IO and it got blocked. Now my problem is, when this process, whatever is running currently, okay, either gets terminated, then in that case I can reuse the space. What if this also goes into a block state? It wants to some IO to be done. Now we are not having any space at all in the main memory for you to bring a new process, even if it is created, or if it already, maybe something is there already and you are not able to create it because there is no space. In that case, what happens is OS will take out the process from the main memory, move into hard disk. Remember, always main memory is limited memory, whereas hard disk could be assumed to be infinite, but it's not reality. Your laptop has a fixed amount of hard disk, but in the server case, or maybe if you go into a Facebook server or Instagram, they don't stop you saying that I don't have space now, don't post anything now. Okay, you keep posting it, they keep adding more servers, more systems, more hard disk, more memory, secondary memory to store all your posts on the Facebook or Instagram. That means it is ever growing every day, every minute. So this secondary storage is practical purposes is unlimited, whereas main memory is limited because the laptop is built for a particular RAM, okay, 8 GB or 16 GB, whatever you have on the system. So how do you now make other processes to run on the system unless you create some space, free space in the main memory? How can you create a free space? You have to remove something which is there. But the problem here is all of them are in block state. That means these processes may come out of the block state and may want to run. So I cannot forcibly kill them, saying that okay, I don't have main memory space, so I will kill you all of you. That's not fair. So what you do is OS, not you, OS does it. It moves those processes into hard disk, and then if it is out of sight, it may forget, right? So it needs to maintain information saying that okay, I know one process was there, its PCB entry was so and so, and it was in a block state and I moved it to hard disk. So that is a different information, because if it is a blocked and if it is available in main memory, no issues. But if it is blocked and then it was moved to hard disk, I need to know that by having a different state associated with that. Because why? If it is in suspend state, I cannot immediately make it to running, because or even I can't make it to ready immediately, because I need to make sure that that image, whatever is there in the hard disk, need to be brought into the main memory before making it ready. So I need a stopgap state where I can keep it here. So in that suspend state, what happens is the process is in uh, it was blocked and then it went into suspend state. That means it was moved from main memory to hard disk. Now, when the event for which it was waiting for is done and it is now available, whatever it was waiting for, how does the OS come to know? Because it is maintaining all the PCB entries, I said that in the OS data structure. Though the process related resident set is moved out of the main memory, doesn't mean that this process is forgotten. OS maintains the information. It's like we moving out of the country to some foreign countries. It doesn't mean that maybe our Airtel or whatever mobile service provider may think that you are out of region. You are no, maybe you are connecting to Orange or some other service provider, and then you will come to know the Airtel or whatever your home location, mobile location connections you have. If you have enabled international roaming, then the local service provider will know where your mobile is. If you have moved to whichever country you are. But suppose you are not enabled international roaming services and you move out of the country, you are lost. As far as the Airtel is concerned or your mobile service provider is concerned, you are now traceable. Your mobile maybe you are switched off because when you got into international airline, you switch off the mobile. After that, it is forgotten. Now it doesn't know, but still it maintains your records of, okay, where, what's your user ID, what is your IMEA number or whatever. And but it knows also that, okay, at this moment, you switched off or you went out of the region of its coverage. When you come back, returning on from the foreign trip, and you switch on the mobile, the service provider catches you. Okay, it knows now, based on the previous record it recognizes your number, your mobile, and in fact your mobile number is what is the most critical thing. You may come with a new mobile from foreign country, and then you may put your SIM on that, and then it doesn't matter whether you are holding the same device or not, but your mobile number is unique, and that's like a PID or a process ID. So when it remembers even though you are not in the uh, its coverage area. Similarly, even though the process is not in the main memory, it is remembered by the OS. When the event for which the process was waiting for is happening, OS will come to know of it, and then it will go to the hard disk. It knows where it has moved it, and then it brings it back to the main memory, and then makes a change of the state to ready. Once it is in ready state, now scheduler runs, and then it can pick up this process to running. So this is the background of what is a suspend state. I hope this is very clear to you. Imagine a situation where main memory is filled with lot of block processes, and you are deciding to OS is deciding to move something out of it. The most least low priority processes may be moved out, so that you can keep having some processes which are in ready state, so that CPU will be utilized. Okay, always OS wants to use the CPU to the maximum extent. How can it do it? Only when it has a lot of ready processes in the system. For that it needs main memory, because residence it has to be brought. For that it has to vacate something. So it's like optimization of the available memory that it has. So it could be, it could also prevent creation of new processes, because if you don't run out of main memory, then you cannot allow any new process to enter the system. Okay, so to make the system efficiency, main memory is so to make the system efficient and responsive, main memory needs to be freed up. Okay, that's all I'm saying. So the transition from any state to exit. Now, one thing what is not shown here is any state to exit is possible. Let me tell you how new state to exit is possible. A process is wants to be created, a PCB entry is created, and then I told that it is going into read the executable file, and it can encounter that executable file, you don't have a execute permission. In that case, whatever you wanted to do will be terminated immediately. It cannot run it, right? Then you will exit. Or the file itself is not there, then also you will exit. The file is corrupted, you are not able to, the OS is not able to read the executable, load it onto the main memory, because the file is corrupted. Then also it will go into re-exit. So this is possible. Now, what are the possible state you can come from ready to exit? Suppose you are ready to run, but you are not running on the CPU, you are there on the system, but administrator of the system, okay, in Linux environment I'm telling you, particularly root user or admin pass, permissions some users are having, IT admin, they may decide to kill all the processes because they want to shut down the whole server. Then all the processes running in the system should be shut down, should be killed before the server is brought down. That means you are switching off the server. In that case, they may kill it, or they may say that, okay, you are not a no you suppose you have paid for some money for service, and then your licensing is ending. So whatever processes belong to your, as a user, all the processes belonging to you will be removed. So these kind of things, irrespective of whatever may be the state of your process, they may be killed. So ready to exit is possible. Is the possibility of running to exit? It is there. Okay, you terminate yourself, or you do some illegal operation, that exception is created, and you, because of that process gets exited. So there is many possibility. Now what about this block to exit? That is also possible. You went to in a sleep state, saying that I am waiting to read or open a file, but the file doesn't exist, or the directory path you gave it doesn't is a valid. It's not a valid path. Then also you went into block state, looking, thinking that you will be, able to open the file, but the file doesn't exist, or you don't have permission to open the file, or the path you gave to reach the file is not, is illegal, or the file is moved somewhere. All these possibilities could lead you to move from block state to exit state, because what happens is error happens, and then that error could be catastrophic, because you may write a code saying that if f open is failing, I want to exit from the system. So that you see, if suppose you want to open a file and then update something on it. Suppose if you are not even able to open the file, what is the point of running further? You might have written the code such a way that if open fails, I want to exit. So in that case also it may go away. Now, what is the possibility of suspend becoming exit? It could be possible that OS moved you out of main memory and it was in the hard disk. During that time, somebody killed you, or sorry, I'm not saying you. The process was killed by someone, or someone. It could be many reasons that the system is maybe overloaded, or system is shutting down, or whatever maybe the reason the process is killed, and it could lead it to exit state. These are all the different ways that any state could lead it to exit state. So that also you should remember is not shown on the diagram for simplicity purpose. Okay. Suspend is reasoning. I have told you it chooses one of the block process to residing in the main memory to change it to suspend state and moves the current process contents to disk. Okay, to free up some space for main memory to add new processes, and then it will be brought back to main memory when that event for which it was waiting for is actually happens. Okay, so priority of the process plays a role here. You may choose the low priority processes in the block state to be suspended. Okay, so I hope this lecture was useful and you could follow all the transitions and possible things that are happening, and what is the OS doing and what is the purpose of the activities that OS is doing. Okay, these are all very important and very interesting to know about it. Okay, so let us catch up in the next lecture. Bye bye.